Hi guys, 6.7 electronegativity and bond polarity. Before we get started, I'm going to suggest that you have a periodic table nearby, your handout, and then also this table of molecular shapes, and I'm going to link that in the module. And they're also found under, if you go on Dropbox, these are both under general resources. Okay, so electronegativity. We are headed towards understanding the polarity of molecules, and before we can do that, we need to understand the polarity of bonds. And those are related to electronegativity. Electronegativity is a unitless number, and they're in the squares here, that describes the ability of an atom to attract an electron. That's what it says here. The ability to attract electrons in a shared chemical bond. It was devised by Linus Pauling. It's a unitless number, and it increases when you go from left to right across the periodic table and decreases as you go down a group. That is because it's for kind of the same reasons that ionization energy has the same trends. So as you go from left to right, there's more protons in the nucleus. They have a greater ability to attract electrons. And as you go down the periodic table, the shells get further and further from that nucleus. And so that outer shell has less of an ability. There's more shielding between it and the nucleus, and has less of an ability to attract electrons. Fluorine is the most electronegative at 4.0, and cesium is the least. And so as you go up and over, electronegativity increases. And so you can imagine that if you have a bond between two atoms of different electronegativities, they might not share electrons equally. So let's look at this example here. Okay, hydrogen has 2.1 on that scale, and chlorine is 3.0. Okay, so we can see from this that that there's a difference in electronegativity for HCl. We have two different molecules here, HCl and H2, or hydrogen. Hydrogen's one of the 7 diatomics. Okay, so and this sort of space filling model is representing the electron density around those two hydrogens. These two electrons here those are the shared electrons in the covalent bond. Now, because these two hydrogen atoms have the same ability to attract electrons, and remember, it's this nucleus pulling electrons and this nucleus pulling electrons to keep them in between their atomic radii. The electron density around the atoms are going to be shared equally, and so this bond, so that everything is symmetric. However, it's a different scenario if we look at HCl. Chlorine has 17 electrons. Hydrogen only has 1. Has 17 electrons, but the important part is it has 17 protons. So imagine there's 17 positive charges trying to attract that electron, but only 1 trying to attract that electron. Well, and that is reflected in these electronegativity numbers. So chlorine, having a greater ability to attract electrons, is going to have more electron density around it. And so think about it this way. Chlorine comes in before the bond. It has 17 protons and 17 electrons, zero-sum charge. But now, when it's in this covalent bond, it's going to take some of the electrons away, some of the electron density away from that hydrogen. So it's not going to win that whole electron like in an ion pair, but it's going to have more than its fair share. So if it has, let's just say, for example, it's getting 30% of the electron from hydrogen. Well, then it's going to have it's going to have 17.3 electrons on average, but only 17 protons. And so it will have a partial negative charge because it's got 17 protons, but slightly more than 17 electrons. Hydrogen started out with 1 proton and 1 electron and 0 charge, but it lost some of that 1 electron on average to the chlorine. And so it's going to have a partial positive charge. And we call this separation of charge a dipole. Dipoles are vectors along the bond angle that reflect a separation of charge. The bigger the difference in electric negativity, the bigger the magnitude of the dipole. And when you have a charge separation, you have a polar bond. Here, things are equally shared with hydrogen, and so this is a nonpolar bond. Okay, so let me see what this is supposed to be showing us. Okay, nitrogen, nitrogen. The electronegativity difference is what's going to tell you whether or not you have a polar covalent or a nonpolar covalent bond. These are examples of nonpolar covalents, and we're going to look at the difference in the electronegativity. The greater the difference, the more polar the bond. Obviously, any diatomic that's homonuclear is going to have an electronegativity of 0. So that would include N2, Br2, I2, F2, O2, 1, 2, and H2. 1, 2, 3, 4, 5, 6. I'm missing one. Chlorine. Those are the 7 diatomics. And they make a 7 on the periodic table. ClBr, chlorine has an electronegativity of 3.0. Bromine has one of 2.8. And so the difference in electronegativity is 0.2. Our rule of thumb is going to be if it's less than 0.4, then we'll consider it nonpolar covalent. HSI is 2.1 minus 1.8, and that difference is 0.3, so that is also nonpolar covalent. And just to be clear, I'm getting these numbers straight from this table. I am not going to expect you to memorize these numbers, but I am going to expect you to know the trend. Given a pair of elements, which one is more electronegative? Famously, this is important in organic chemistry, CH is a nonpolar bond. So anything that is made up, any hydrocarbon, anything only made up of carbons and hydrogens will be considered nonpolar covalent. Carbon has a electronegativity of 2.5, hydrogen is 2.1, so 0.4. Okay. Other examples that are polar would be oxygen chlorine, chlorine carbon, oxygen sulfur, and I'm going to say CO and CN are going to be important for you guys because those are the ones that are found in biomolecules. So oxygen is 3.5, chlorine is 3.0, that's 0.5. Chlorine and carbon, 3.0 minus 2.5, that is 0.5. O and S, 3.5 minus 2.5, that is 1.0. That's pretty polar. C and O, let's see. C is carbon is 2.5, oxygen is 3.5, so that's 1.0. And again, it's going to be the absolute value. The sign is meaningless. We need to get the number for nitrogen. Let's see. Okay, so carbon, again, 2.5. Nitrogen is 3.0. So that's only 0.5, but so it's at the minor end of polar. And so in the range between 0.5 and 1.8, those are considered covalent and polar. When you get beyond 1.8, we consider it to be ionic. If I give you these examples, I could ask you which ones are the most polar. Well, those would be the ones with the biggest numbers, so OS and CO. I could ask you what's more polar, a CO bond or a CN bond, and you would say that CO is, because the electronegativity difference is 1.0 versus 0.5. Okay, so here are the dipoles. So the more electronegative element gets the partial negative. The least electronegative element gets the partial positive. And so these are examples of polar covalent bonds and their dipoles. And the way I remember how to draw the arrow is that little plus sign at the end of the arrow goes with the plus sign for the partial positive charge. Okay, now ionic bonds is when you have a difference in electronegativity of greater than 1.8 greater than 1.8. And examples we have here are CLK, N, and A. Not that we see these, but that would be 3.0 minus 0.8, which is 2.2, and 3.0 minus 0.9 is 2.1. It's worth pointing out that these are things that are going to be coming from opposite ends of the periodic table. Potassium's on the far left, chlorine is on the far right. Sodium is on the far left, nitrogen is towards the right. So things from opposite sides of the periodic table. Okay. So if you want to pause, you can read this. And here's a graphic description of the bond types and the electronegativity differences. Right, so this one is showing equal electron density on both sides of the bond. This one is showing a polarization. There's still overlap in between, but there's more electron density here, and so it's going to have the partial negative. An ionic bond is represented by non-overlapping spheres. Okay. So let's look at these. Predicting bond type and electronegativity differences. This is H2. So that's an H bond. The electronegativity difference is 0, so it's going to be nonpolar covalent. BrCl, the electronegativity difference there is 3.0 minus 2.8, which is 0.2, nonpolar covalent. HBr, 2.8 minus 2.1. The 2.8 is the bromine. And the difference is 0.7, which is greater than 0.5, so it's polar covalent. HCl. Hydrogen is 2.1, chlorine is 3.0. So this is a polar covalent bond. NaCl would be 3.0 for the chlorine minus 0.9 for the sodium, 2.1. That's going to be ionic. MgO, 3.5 for the oxygen minus 1.2 for the magnesium is 2.3. That will be ionic. Okay, you guys can do those. Let's look at shapes and polarity of molecules. Okay, so in a molecule of methane, CH4, the central atom is bound to 4 atoms. The best geometry for minimal repulsion is tetrahedral with bond angles of 109 degrees. So basically, when we are looking at shapes, it is called VSEPR, valence shell electron pair repulsion. What you're going to do is basically look at the number of things coming off a central atom and determining what geometry will give you the biggest separation. We'll go here. And like I said, valence shell electron pair repulsion, VSEPR, states that electron groups are arranged as far apart as possible around the central atom. That states that the specific shape of a molecule is determined by the number of atoms attached to the central atom. And really, by atoms, it's atom groups, or number of what we will call electron groups. And for this, we have unbonded pairs of electrons that they count as an electron group. A single bond counts as an electron group, a double bond counts as an electron group, and so does a triple bond. They all count as one group because they move together. Okay. Here is CO2. Oh, and let me just, where is my, oh, here it is. This table summarizes everything that I'm about to go over in one place and gives you an example. But let's look at it one at a time. Okay, CO2. We know that the Lewis structure of CO2 is this. Our central atom is the carbon. Only central atoms have geometry that we're going to determine. And there are 2 double bonds coming off of that central atom. Each of those double bonds counts as one electron group. So CO2 has 2 electron groups. And the farthest part, this oxygen and this oxygen can get away from each other because there's electrons there, is 180 degrees. There's no further away apart that they can get. And so we call this shape linear because they form the 3 atoms in the angle, the 2 oxygens and the carbon form a line. So that shape is called linear. And that's what's shown in this first row of the table. We call the number of electron groups is the steric number, and this has only 2 groups. Okay. Now there's different ways and there's only one kind with 2 electron groups. If we look at a molecule like formaldehyde, which is shown here, there's 3 different electron groups. Again, we're only looking at the angles around that central atom, the carbon. So there's 3 electron groups, the 2 hydrogens plus the double bond to oxygen. Well, the furthest apart they can get is forming this trigonal planar structure with an angle of 120 degrees. And so that is the name of the geometry for this molecule. Now, it's possible to have something that has, so this is 3 electron groups. And that central atom has no unbonded pair of electrons. But you can also have 3 electron groups where it's bonds to 2 different things and an unbonded pair of electrons. This unbonded pair of electrons influences the geometry of the molecule because it causes repulsion to those other electron groups. So what we would say is that this has 3 electron groups. In that table, we would say it has a steric number equal to 3, but it has 2 bonds and 1 unbonded pair. And so we count that as an electron group, that is an electron group, that is an electron group. And so the angle here is 120 degrees. And the name of that molecular, so the electronic geometry is still trigonal planar. That's where that 120 degree angle is. But if you're looking just at the molecule, there's nothing up here. And so this looks bent. And so the name of this shape is bent 120. And if I go back to this table, this is trigonal planar. The electronic geometry is trigonal planar because there's 3 atoms around it, no unbonded pair, and so we say 3, 0. This molecule, SO2, has 2 bonds and 1 unbonded pair, so we say it's got a steric number of 3, but one central, 1 pair of unbonded electrons on the central atom. And so the electronic geometry is trigonal planar. The molecular geometry is bent, and that angle is 120. Okay, so that's steric number 3. Now there's possibilities for molecules with 4 electron groups, and methane is the example. Now, when I'm meeting in person, I usually hand out some kind of sphere with toothpicks, and I have people tell me how far apart can they get the toothpicks. And invariably, most of the class will put them in a cross like this and tell me that 90 degrees is the best angle you can get. It's close, but it does not make use of the 3rd dimension. So if you put it into 3 dimensions, you have what's called a tetrahedral shape, and you can actually get a little bit further apart. And so that angle is 109 degrees. The way this is drawn, the lines represent bonds that are in the plane of the paper. The dotted wedge means it's going back behind the paper. And the solid wedge means it's coming out towards us. Hopefully you guys have molecule kits and you can play around with that maybe from the lab. Okay, so now you can imagine it's possible to have a central atom with 4 electron groups, but also have an unbonded pair of electrons, and ammonia is one of those. The Lewis structure for ammonia looks like this, and so it has 4 electron groups, 1, 2, 3, and then the unbonded pair of electrons. So its electronic geometry is going to be tetrahedral. However, there's no atom up here, and so its molecular geometry is called trigonal pyramidal. And the angle is going to be 109 degrees. Okay, now it's also possible to have 4 electron groups, and 2 of them are unbonded pairs, and water turns out to be an example of this. So here's the water-Lewis structure. There's the 4 electron groups. 1, 2, 3, 4. But 2 of them aren't to any atoms. And so we say that the electronic geometry is tetrahedral. The molecular geometry is bent, but this is bent 109. And I do expect you to know the difference between bent 109 and bent 120. And so these are all summarized here. Here's the 4. All of these have steric number of 4. If you have a steric number of 4, always the electronic geometry will be tetrahedral, but the molecular geometry depends on the number of unbonded pairs. If you have 0 unbonded electrons, and this is true for any shape, if there's no unbonded electron pairs, the molecular geometry and the electronic geometry are the same. But if there's an unbonded pair for tetrahedral, it becomes pyramidal. And if there are 2, it becomes bent, or it is bent. And they have a similar table here. Let me see what this example is. CO2, H2CO, SO2, CH4, NH3, H2O. Bond angle 180, 120, 120, 109, 109, 109. Okay, so let's predict the molecular shape of H2S. Okay, so first thing to do is count the number of electron groups. There's 1, 2, 3, 4. So we know that the electronic geometry is going to be tetrahedral. The molecular geometry is going to be bent. And if you look on that table, you should be able to find it. This is an example of 4, 2. And so the angle is 109. Okay, let's look at PF3. The other example they have here is water, which we've already done. Okay, so PF3, in order to know whether or not there's an unbonded pair of electrons on the central atom, or if you have double, you need to do the Lewis structure. So phosphorus has 5 valence electrons. Fluorine has 7, but there's 3 of them, so it's 21. 26 total. By the way, if you ever get an odd number of valence electrons, count again, because it's very rare. Okay, so phosphorus is going to be my central atom. Fluorine, fluorine, fluorine. Put in my double bonds, -6. Now I've got 20, so fill in the outer valences. That used 18, so I have 2 left. Oops. So that phosphorus has an unbonded pair of electrons. So how many electron groups do I have? I've got 1, 2, 3, 4. So the electronic geometry is tetrahedral. The molecular geometry is going to be pyramidal. Okay, if we do the Lewis structure, of carbon tetrachloride, it's going to be this. So this one is going to be, there's no unbonded pairs of electrons on that carbon in the center, and so the electronic geometry and the molecular geometry are going to be the same. And it will be tetrahedral. Here's my table again. State the number of electron groups in lone pairs and use, oh, we already done it. Okay. It's still part of the solution. Okay, now we have shapes of molecules. We know about bond polarity. Now we have to apply this to molecular polarity. I'm going to fill in some stuff here. Okay, so molecules, any diatomic molecule, any homonuclear diatomic molecule, anything that is the same atom in a diatom is going to be nonpolar, right? So this would include N2, Cl2, F2. Those are all, and I2. Those are all going to be nonpolar because they do not have polar bonds. So any molecule that only has nonpolar bonds, that molecule will be nonpolar. However, it is possible to have a molecule that has polar bonds but is nonpolar. And two examples are actually shown here. One is CO2. CO2 is linear, right? And there's a dipole this way and a dipole that way, but they are equal and opposite in magnitude, and so they cancel out. So CO2 is nonpolar. Carbon tetrachloride also has polar bonds. The CCl bond is polar, but they all cancel. And so carbon tetrachloride is also nonpolar. So these are two molecules that have polar bonds but are nonpolar. And the rule of thumb for this actually is that if you have, I'm going to write this out because it's worth writing out. Okay, so if you have a central atom with no unbonded pairs of electrons, and all bonds are to the same atom, this molecule will be nonpolar. So CF4, same thing. There's no unbonded electrons on that central carbon. Everything's to fluorine. All the dipoles will cancel. So this is nonpolar. BCl3. Also nonpolar. There's no unbonded pairs on the central atom, and so this will be nonpolar. But if you have ammonia, now all of a sudden all the dipoles don't cancel. I have a dipole here, a dipole here, and a dipole here, but there's nothing up here. And so this molecule is polar. And this is an example of, let me see if I can do this efficiently. Oop. Okay, we have a central atom with unbonded pairs of electrons. That will make the molecule polar. Water's another example. It has these unbonded pairs, and so the dipoles don't cancel, and water is polar. This is going over ammonia. Okay, let's look at OF2. I'm going to add a page. Okay, OF2. 6 plus 14 gives us 20 electrons. O, F, F, minus 4 gives us 16. 1, 2, 3, 4, 5, 6. Minus 12 gives us 4 left over. Okay, so this is the structure for OF2. And if we look at the geometry of our central atom, we see 4 electron groups. 2 of them are unbonded pairs. Fluorine's the most electronegative element, so our dipoles are going to be like this. And so this molecule is going to be polar. So what did we do? The first thing we did was we did the Lewis structure. Once we did the Lewis structure, we figured out the geometry. After that, you look for polar bonds. And then you determine, do dipoles cancel? Do dipoles exist? And if so, do they cancel? If they don't cancel, then it's polar. We look for polar bonds. If there's no polar bonds, then it's nonpolar. If there are polar bonds, maybe. We have to go to step 4. That's the answer to that. Okay, IMFs. Intermolecular forces. You're going to hear me say IMF a lot. These are attractive forces between molecules. And so if we're looking at this, here we have a covalent bond, here we have a covalent bond, covalent bond. Those are not IMFs. IMFs are the interactions between molecules. So these are non-covalent interactions, and they're usually indicated with dotted lines, especially hydrogen bonds. And so if we look, this is 2 water molecules. We know that there's a dipole along the OH bond, which gives us a partial positive on the hydrogen and a partial negative on the oxygen. And so those partial charges are opposite, they attract. And that creates what we call a hydrogen bond. There are lots of hydrogen bonds among water molecules, and because of that, water molecules tend to stick together, which you see with capillary action, but also it gives water a very high boiling point for a liquid. So there are different kinds of intermolecular forces. When there are dipoles present in a collection of molecules, they will have dipole-dipole interactions. This dipole is interacting with that dipole, positive to negative, and we call that a dipole-dipole attraction. A hydrogen bond is a dipole-dipole attraction. It's a special case of it. Hydrogen bonds can only happen when the hydrogens are covalently bonded to F, O, or N. And really, in practicality, the only ones that matter are N and O, because there's only one example of fluorine. And so, because this hydrogen is covalently bound to that nitrogen, it is capable of donating a hydrogen bond. That nitrogen has a lone pair and a partial negative charge, and so it can accept the hydrogen bond. A weaker force are these dispersion forces. Dispersion forces are weak attractions between nonpolar molecules. And these are actually temporary dipoles. For the longest time, I could not figure out what that means. So these are nonpolar molecules. What happens is, If they are very, very close together, like their electron clouds are almost touching, then you get synchronization in the movement of the electrons. And so for a moment, there might be a partial negative here and a partial positive here. And this partial positive is going to cause a partial negative here. And so you get this oscillation of negative to partial negative to partial positive dipoles, but it may be in the opposite direction and instantaneously later. So these are by far the weakest. These are the weakest intermolecular forces, but they are the most prevalent. So just to put a face on it, the strongest interaction we would call an ion pair. And those have about 90 kilojoules per mole of attraction. If you have a dipole, a dipole-dipole interaction, that's about 9 kilojoules per mole. The hydrogen bond is actually about 20 kilojoules per mole. These dispersion forces are about 0.2 to 0.9 kilojoules per mole. So they are far weaker than the ion pair and also weaker than the dipole-dipole interaction. There's like a factor of 10 in the strength. The stronger the intermolecular forces, these IMFs, the more the molecule will stick together and resist. It will require more energy to undergo a phase change. So melting points of compounds are related to the strength of their IMFs. Ionic compounds have the highest melting points because they have ion pairs, which are, like I said up here, are quite a bit more strong than dipole-dipole interactions. Okay, so let's fill this in here. MgF2, so that's magnesium fluoride, has a melting point, and these are in Celsius, of 1248. Sodium chloride, 801. Molecules that have dipole-dipole attractions, minus 51, again degrees C, minus 89, minus 115. So big difference between ionic molecules and ones with polar molecules with dipole-dipole interactions. The melting point for water is 0 degrees C, and for ammonia is minus 78. Nitrogen containing hydrogen bonds are weaker than those with oxygens. Okay, so if you have only dispersion forces, then the melting point is very low. Again, degree C. And this is a nice representation of the strength of interactions and a summary of how they're classified. Okay, I'm going to stop there. You made it through all the exam 1